Dr. Esther Trufan, and in this video, I am going to demonstrate an equilibrium experiment. In fact, we will be looking at the solubility constant of carbon dioxide in water and how we can impact that solubility by raising and lowering the temperature associated with it. So for this experiment today, we're going to use some seltzer water, which is essentially carbon dioxide dissolved in water. And it is at its saturation limit at whatever temperature this can is at. We also need some indicator. And for our equipment, we will be using two 250 milliliter Erlenmeyer flasks. We will need a balloon. This could be of any color. For today, I am using green. We will use a 50 milliliter graduated cylinder, a cup, a straw, and then a white paper to trace our color changes a little bit more closely. Additionally, we will need a hot bath, as hot as we can get it. Here I have two beakers with water in them that were already heated. And we will need an ice bath that I set up here in this bin. It's just ice. I can always add a little bit of water to make the connection between the cold environment and the beaker or Erlenmeyer more efficient. So let's get started. The first thing we're going to do is open up our seltzer water. Yes. We will transfer some of it into the cup. That should be a sufficient amount. Then we are going to use our indicator solution, mix it in, to give it a dark enough color so that we can see any color changes associated with it. Then we're going to measure out approximately 50 milliliters of our indicator and seltzer water combination. Now, I am aware that the seltzer water has bubbles in it, and in this case, we're not going to wait for the bubbles to stop. That is why it is approximately 50 milliliters of solution. This is approximately 50 milliliters. I will transfer it into my first Erlenmeyer. And I will do the same to the second. Here I have our second 50 milliliter solution of seltzer water and indicator. With that, I am done with the graduated cylinder and I can set it aside. Next, I'm going to take the balloon and put it on top of one of the Erlenmeyer flasks. Now, I will keep my original cup as the reference color of what seltzer water will do if we don't do anything to it. This will be our reference color moving forward. Now I will take my two Erlenmeyer flasks and I will lower them into the hot water bath. I will keep it there for about 5 minutes. It has been approximately 15 minutes since we placed our Erlenmeyer flasks inside our hot water baths, and there is a noticeable color change between the two Erlenmeyer flasks. So I'm going to extract each one and we will compare it visually in terms of color to our reference cup. So first, and this is where we want to be somewhat careful, these Erlenmeyers are quite hot. I extracted the Erlenmeyer that contains the seltzer water with the indicator solution that we had the balloon connected to, and this way any gas that evaporated in the process was contained in the balloon that is attached. In the second Erlenmeyer flask, we had the seltzer water solution with the indicator, and in this case any gas that was released in the heating process went out in the atmosphere with no chance of return. So next we're going to transition both of our Erlenmeyers into an ice water bath, because this way we're going to cool their temperature and get back to hopefully the solubility of carbon dioxide being higher in water than at higher temperature. So we submerge both our solutions in the ice water, and we give it a couple minutes to see what happens. It has been approximately 5 minutes since we placed our Erlenmeyer flasks inside our ice water bath, and both solutions have cooled down substantially. I will extract both of them. And once again, we can visually compare the two Erlenmeyer flask colors compared to the reference. If we were to do nothing to it, this is the color of the solution that we should have. When we heated it, and there was no way to recapture the carbon dioxide and cool it back into the solution, then it turned more bluish, and that color did not change despite us putting it back in the ice bath. When we attached the balloon to the Erlenmeyer, even though we heated it just like the other, the carbon dioxide was contained inside the balloon, and then when we cooled it down, the carbon dioxide from the balloon went back into the solution. The environment around it was more rich in carbon dioxide in the second case. So now let's see if this is just a fluke or if this is a repeatable experiment. We're going to next remove the balloon from our Erlenmeyer and place it once again in the hot water bath. We will keep it there for at least 5 to 10 minutes to see if we can achieve the same color change that we achieved with the other Erlenmeyer that was exposed to the air. In the meantime, if it is true that the availability of carbon dioxide caused our balloon-connected Erlenmeyer flask to maintain its color a lot closer to this pinkish range, then with the addition of more carbon dioxide, we should be able to turn our solution to the same color. And one way to add carbon dioxide to it would be to find some dry ice and add it in, or absent dry ice, we can always use the natural biology of human beings where we breathe in more oxygen and we breathe out more carbon dioxide. So for this part of the experiment, we're going to use a straw, and we're going to submerge one end of the straw into our solution, and on the other end, we just blow until we see some change. Or until we get tired. That is a lot closer to purple, and if you remember, we originally started with blue. It has been approximately 10 minutes since we submerged our Erlenmeyer inside the hot water bath, and we are already noticing a color change. It has shifted from more a pinkish purple to a closer to bluish purple. So from this experiment, we should be able to derive some conclusions. If our red cabbage solution is turning bluish and then later other colors, that is going to be an indication that it is shifting closer to neutral and potentially further from there. However, if it is turning pink from previous experiments, we should know that anything that is slightly acidic or somewhat acidic will change the color of the red cabbage solution more pink. Carbon dioxide is an acidic oxide. When it dissolves in water, it will react and it will produce carbonic acid, which is a weak acid. And weak acids are going to cause a pink color to appear when using a red cabbage indicator solution. The absence of that is going to leave us with a more purple or bluish purple color.